my name is Hannah McKenzie, and I am a master's student in the lab of Dr. Reed Johnson at The Ohio State University. Today I'm going to talk about my work developing a new method to detect foraging honeybees, as well as the challenges of developing this new technology. My area of interest is honeybees as pollinators of soybeans, which are a growing industry in the United States and the world. In 2020, soybean exports from the U.S. were valued at $25.7 billion, making it the country's #1 agricultural export. In 2021, soybeans covered 87.6 million acres of agricultural land in the U.S. I'm interested in how pollination can help improve the sustainability of production in this growing industry. Several studies show a positive correlation between soybean yield and honeybee pollination, with yields increasing in a range of 13 to 21%. That is an additional profit of $59 to $170 per hectare, or an annual addition of $6.1 to $17.4 billion to the global economy. Unfortunately, the industry is faced with a problem in the realm of pesticides. These impacts of pollination are often overlooked in self-pollinating plants like soybeans, so it is likely that growers are applying pesticides to their fields when bees are active. For growers to incorporate pollination into IPPM, or Integrated Pest and Pollinator Management, they must answer the question of when bees are in their fields to avoid exposing them to pesticides. The problem is that growers don't always know, and it can be difficult to find out using existing methods. These existing methods for pollinator detection include yellow pan traps and manual collection or observation, but there are limitations to these methods that make them ineffective for large-scale detection of honeybees and field crops. Yellow pan traps tend to favor smaller bees, such as sweat bees, over larger bees, such as honeybees. Manual techniques are better for detecting larger bees, but require large time and labor investments. A new method is necessary to accurately and efficiently detect honeybees in large crop systems. My objective is to develop a new methodology that effectively detects honeybee activity in soybean fields without large labor and time investments. I hypothesize that field microphones will detect quantifiable honeybee activity through wingbeat bioacoustics. For this study, I placed microphones in soybean fields to record audio of honeybee activity. I then analyzed this audio as spectrograms, which are visual representations of sound. I can identify honeybees by looking for their specific wingbeat frequency, which is approximately 234 Hz. This is the current extent of my research, but after I address the challenges of this new method, I hope to implement machine learning software to recognize honeybee wingbeats and make analysis much more efficient. I first collected preliminary data in blooming spirea next to one of our apiaries in Worcester, Ohio. Once I confirmed that my microphones could successfully pick up bee wingbeats, I moved to my main data collection in actual soybean fields. This is one of the 4 soybean fields in Worcester, Ohio that I used for this study. I chose a transect starting at the edge of the field and placed microphones at 5, 15, 25, and 35 meters along that transect. I placed the microphones at a height that was level with the highest blooming nodes of the soybeans, and after I collected all my data, I removed any audio recorded between sunset and sunrise from my analysis, since honeybees don't forage in the dark. The results of this study were promising, but there are still challenges to address before this method is viable in large field crops. Today I will discuss 3 of the challenges I encountered: wind interference, sound differentiation, and rain, as well as my solutions to each of these challenges. I will then discuss my overall results and my next steps. This is an example of a spectrogram visualizing a small segment of audio in the software program Audacity. The x-axis shows the passing of time, while the y-axis shows the frequency of the sound in hertz. The colors on the spectrogram indicate the intensity of the sounds in decibels, with purples and reds showing less intensity and oranges and whites showing higher intensity. This is what a bee looks like on a spectrogram, and what I expected to see in my preliminary recordings of spirea. Unfortunately, most of my audio was lost to wind interference, which looks like this. As you can see, the wind visually blocked out any wing beats from bees. I overcame this challenge by covering the exposed microphones with a foam windscreen. This prevented air currents from striking the microphones directly and effectively removed wind interference from my audio without compromising the microphone's capacity to pick up other sounds. With wind interference removed, I was able to successfully record green beats with my microphones. This is the target range for honeybees. As you can see, I detected several honeybees just in this small segment of audio. Interestingly, I also detected several wing beats that fell outside the target range for honeybees. This aligns with my visual observation of several other pollinators on the spirea, including other bees, wasps, and hoverflies. This diversity in wing beats presents another challenge in differentiating sounds that look similar on a spectrogram. For example, some of the wing beats appeared to cover multiple frequency ranges, likely due to sound refraction. Other wing beats overlapped with each other because the microphone picked up more than one pollinator species at the same time. Other segments of apparent bee activity actually turned out to be interference from ground and air traffic. I was easily able to differentiate these sounds via manual listening, but these overlaps and interferences may be more difficult for a basic algorithm to interpret. I'm hopeful that machine learning software will be able to recognize these patterns and accurately differentiate honeybees from other pollinators and human noise pollution. With my microphones working, I moved them to the soybean fields, where I encountered my third challenge, the threat of rain. The microphones I used in this study were not waterproof, so I had to remove them from the fields early if there was a chance of rain. I overcame this challenge by protecting the microphones with 3D printed rain covers. When placed out in the rain, these covers successfully protected the microphones from water damage. They even worked on windier days, since the microphone is located at the top of the device where it is most protected by the cover. After I collected all my data for the season, I examined a subset of data and found some interesting results. In one of the fields, L68, there was an average of 49.5 occurrences of my target frequency per hour. Upon listening to the audio, I found that 73% were caused by ground traffic, 27% by air traffic, and 0% by bees. I thought it might be possible that the intensity of the ground traffic drowned out the wing beats of any bees, since this field was located right along Route 250. So I also examined a subset of data from field A11, which was located furthest from Route 250. I did indeed find a decrease in ground traffic, with there now only being an average of 13.2 occurrences of my target frequency per hour. However, 20% were now caused by ground traffic, 80% by air traffic, and still 0% by bees. I found this strange because I was clearly able to detect many pollinator wing beats in spirea with these same microphones. Upon examining the spirea data again, I found that a majority of the frequencies were caused by honeybees or other pollinators, with only 12% coming from air and ground traffic combined. One possible explanation is that there were no bees present in the subset of data I examined. It has been shown that soybean attractiveness to honeybees varies greatly, depending on several factors, such as soybean variety and day and night temperatures. It is possible that the fields and days that I analyzed were less attractive, so there were not enough bees in the fields for my microphones to detect. I still have more data to examine, and I suspect that I will find bee activity in audio that was recorded under more attractive conditions. Another possible explanation is that this is a limitation of my microphones not being sensitive enough to detect bees that are more spread out in a large monocrop. One possible solution is to use parabolic microphones, which are only sensitive to sounds in one direction, but are much more sensitive to distant sounds, and are often used in nature recordings. These may be better for detecting bees in a large range. In conclusion, developing a new method and technology such as this one is something that requires patience and problem solving. I've already addressed several challenges, and my next steps are to address the challenges that will remain. I will explore how machine learning might assist with differentiating similar sounds. I will continue to improve my technology and examine my remaining data to successfully detect bees in soybeans. I can also investigate how this technology might be used to identify different pollinator species by their specific wing beat frequencies and patterns. I'm determined to learn from and overcome these challenges and continue developing this methodology so that growers will have access to a new technology, one that can increase the efficiency of soybean production and support the sustainability of IPPM practices by protecting honeybee health. I would like to thank the Ohio State University, the Johnson Lab, my Student Advisory Committee, and my funding sources for supporting this project. I would also like to thank the soybean growers of Worcester, Ohio, for allowing me to collect data in their fields. Thank you so much for your attention today. If you have any questions, please feel free to email me at mckenzie.387@osu.edu.